Quantum sensors represent one of the most exciting and rapidly developing frontiers in modern science and technology. They harness the unique properties of quantum mechanics, such as superposition, entanglement, and quantum tunneling, to achieve levels of sensitivity, precision, and accuracy that are unattainable with classical sensors. As we stand on the threshold of new technological revolutions, quantum sensors are already beginning to transform fields as diverse as navigation, medicine, environmental monitoring, fundamental physics, and even everyday consumer electronics. To appreciate the significance and potential of quantum sensors, it is essential to understand both the scientific principles that underpin their operation and the myriad ways in which they are being applied. At the heart of quantum sensing lies the exploitation of quantum states, conditions in which particles such as atoms, electrons, or photons exist in ways that defy classical intuition. In classical physics, the state of a system can be described by definite properties such as position and momentum. Quantum mechanics, however, allows for much richer behavior. Particles can exist in superpositions, meaning they can be in multiple states at once, and can become entangled, so that the state of one particle is intrinsically linked to the state of another, no matter how far apart they are. These phenomena are not just theoretical curiosities. They can be harnessed to probe the world with unprecedented detail. One of the earliest and most influential applications of quantum sensors is in the field of atomic clocks. Traditional clocks, such as those based on mechanical oscillators or quartz crystals, are limited by the precision with which their physical components can be manufactured and maintained. Atomic clocks, by contrast, use the quantum transitions of atoms, most commonly cesium or rubidium, as their timekeeping mechanism. The frequency of these transitions is governed by the fundamental laws of physics and can be measured with extraordinary precision using techniques such as laser cooling and microwave interrogation. As a result, atomic clocks have become the backbone of global positioning systems, GPS, telecommunications networks, and financial systems, enabling synchronization at the nanosecond level and underpinning much of modern infrastructure. Beyond timekeeping, quantum sensors have found critical roles in measuring magnetic and electric fields, acceleration, rotation, temperature, and even gravitational forces. Magnetometers based on quantum effects, for example, can detect minute changes in magnetic fields, down to the femtotesla range, 1/4,000,000th of a Tesla. These devices often rely on the behavior of electron spins in materials such as diamond, where nitrogen vacancy, NV, centers serve as highly sensitive probes. By optically addressing and reading out the spin state of these defects, researchers can map magnetic fields with exquisite spatial resolution, opening up new possibilities for imaging neural activity in the brain, detecting hidden defects in materials, and searching for new physics beyond the standard model. Similarly, quantum accelerometers and gyroscopes leverage the wave nature of matter, as described by the famous de Broglie hypothesis. In these devices, clouds of ultra-cold atoms are manipulated with lasers to form matter-wave interferometers. When the device is accelerated or rotated, the interference pattern shifts in a way that reveals the magnitude and direction of the motion. Because atomic matter waves are much less susceptible to environmental noise than classical mechanical components, quantum inertial sensors promise to revolutionize navigation, especially in environments where GPS signals are unavailable or unreliable, such as underwater, underground, or in space. The sensitivity of quantum sensors also makes them powerful tools for probing the fundamental laws of nature. For instance, experiments using atom interferometry have set stringent limits on possible violations of Einstein's equivalence principle, the foundation of general relativity, which states that all objects fall at the same rate in a gravitational field, regardless of their composition. By comparing the free fall of different types of atoms in a precisely controlled environment, physicists can test whether gravity acts universally on all forms of matter. Similar techniques are being used to search for dark matter and dark energy, the mysterious components that make up most of the universe yet remain undetected by conventional means. In medical imaging, quantum sensors are poised to bring about a new era of diagnostics and research. Magnetic resonance imaging, MRI, already exploits quantum phenomena, specifically the alignment and manipulation of nuclear spins in a magnetic field. Recent advances in quantum magnetometry, particularly those using NV centers in diamond, have enabled the detection of magnetic fields generated by single neurons firing in real time, potentially paving the way for non-invasive brain-machine interfaces and early diagnosis of neurological disorders. Quantum-enhanced sensors can also improve the sensitivity and resolution of other imaging modalities, such as positron emission tomography, PET, and optical coherence tomography, OCT, leading to earlier detection of diseases and more effective treatments. Environmental monitoring stands to benefit enormously from quantum sensing technologies. Precise measurement of gravitational gradients, for example, can reveal underground water sources, mineral deposits, or signs of geological instability. Quantum gravimeters, which measure the local acceleration due to gravity with unprecedented precision, are already being deployed to monitor volcanoes, track groundwater depletion, and assess the structural integrity of dams and bridges. Similarly, quantum-based gas sensors can detect trace amounts of pollutants or greenhouse gases, providing early warning of environmental hazards and helping to enforce environmental regulations. The impact of quantum sensors extends into the realm of industrial and consumer technologies as well. In manufacturing, quantum sensors enable the detection of tiny defects in materials, improve the calibration of machinery, and enhance the precision of quality control processes. In the automotive industry, quantum-enhanced gyroscopes and accelerometers could lead to safer and more reliable autonomous vehicles, capable of navigating even in challenging conditions. Consumer electronics may soon incorporate quantum sensors for applications ranging from indoor navigation to augmented reality, offering new experiences and capabilities to end users. Despite their remarkable promise, quantum sensors face significant challenges on the path to widespread adoption. Many quantum systems are extremely sensitive to environmental disturbances such as temperature fluctuations, electromagnetic noise, or mechanical vibrations. Isolating and controlling quantum states often requires complex and expensive equipment, such as cryogenic refrigerators or ultra-high vacuum chambers. Scaling these technologies down to portable, robust, and cost-effective devices suitable for mass deployment is a major engineering challenge. Nevertheless, recent advances in materials science, photonics, and microfabrication are steadily overcoming these obstacles, bringing quantum sensors closer to practical reality. Another key challenge lies in the readout and interpretation of quantum signals. Quantum measurements are inherently probabilistic, and extracting meaningful information often requires sophisticated data analysis techniques, including machine learning algorithms and advanced signal processing. Furthermore, integrating quantum sensors with classical electronics and communication networks demands seamless interfaces and protocols, ensuring that the quantum advantage is preserved throughout the measurement chain. Interdisciplinary collaboration is essential for the continued advancement of quantum sensing. Physicists, engineers, chemists, computer scientists, and domain experts must work together to design, build, and deploy quantum sensors tailored to specific applications. Governments and industry are increasingly investing in quantum technologies, recognizing their strategic importance for national security, economic competitiveness, and scientific discovery. International collaborations, such as the Quantum Flagship in Europe and the National Quantum Initiative in the United States, are fostering innovation and accelerating the translation of laboratory breakthroughs into real-world solutions. Education and workforce development are also critical components of the quantum sensing ecosystem. As quantum technologies move from the laboratory to the marketplace, there is a growing need for professionals who understand both the underlying physics and the practical aspects of sensor design, fabrication, and deployment. Universities and training programs are beginning to offer specialized courses and degrees in quantum engineering, equipping the next generation of scientists and engineers with the skills needed to drive the field forward. Looking to the future, the potential applications of quantum sensors are limited only by our imagination. In space exploration, quantum gravimeters and atomic clocks could enable precise navigation and mapping of distant planets and moons, while quantum magnetometers might detect subtle signatures of extraterrestrial life or geological activity. In biology, quantum sensors could unravel the mysteries of molecular dynamics and chemical reactions at the single molecule level, leading to new drugs and therapies. In security and defense, quantum sensors could detect stealthy submarines, hidden weapons, or clandestine communications, enhancing situational awareness and deterrence. Perhaps most intriguingly, quantum sensors may help unlock new realms of fundamental physics. By pushing the boundaries of measurement precision, they could reveal previously unknown particles, forces, or symmetries, shedding light on the deepest questions about the nature of reality. Already, quantum sensors are being used to search for actions, hypothetical particles that could explain dark matter, test the constancy of fundamental constants, and probe the interplay between quantum mechanics and gravity. To achieve these ambitious goals, continued investment in research, development, and infrastructure is essential. This includes not only funding for basic science and technology development, but also support for pilot projects, test beds, and demonstration platforms that bridge the gap between the laboratory and the field. Intellectual property frameworks, standards, and regulatory policies must evolve to accommodate the unique characteristics of quantum technologies, ensuring that innovation is rewarded while public interests are protected. Public engagement and outreach are also important, as quantum sensors become more integrated into daily life. Clear communication about the benefits, risks, and ethical considerations of quantum sensing will help build trust and ensure that these powerful tools are used responsibly. As with any transformative technology, there are potential concerns about privacy, security, and unintended consequences. Proactive dialogue among stakeholders, including scientists, policymakers, industry leaders, and the public, will be vital to navigating these challenges and maximizing the positive impact of quantum sensors. In summary, quantum sensors represent a paradigm shift in our ability to measure and interact with the world. By leveraging the strange and counterintuitive features of quantum mechanics, they offer unprecedented sensitivity, precision, and versatility across a vast array of applications. From timekeeping and navigation to medicine, environmental monitoring, industry, and fundamental science, quantum sensors are poised to reshape our technological landscape and deepen our understanding of the universe. While significant challenges remain, the pace of progress is accelerating, driven by advances in science, engineering, and interdisciplinary collaboration. As we continue to explore the quantum frontier, the possibilities for discovery and innovation are truly limitless. At the core of quantum sensing lies the manipulation of quantum coherence and entanglement, resources that are fragile but immensely powerful. Quantum coherence refers to the ability of a quantum system to maintain a well-defined phase relationship between different states, enabling interference effects that can be exploited for enhanced measurement sensitivity. Entanglement, on the other hand, allows multiple particles to behave as a single, inseparable entity, enabling collective measurements that scale favorably with the number of particles involved. By carefully preparing, controlling, and measuring these quantum resources, scientists can surpass the so-called standard quantum limit, achieving measurement precisions that grow with the square root, or even linearly, in the case of entangled states, of the number of particles or photons used. One striking example of this principle is the use of squeezed states of light in optical interferometry. In a traditional interferometer, such as those used in gravitational wave detectors like LIGO and Virgo, the sensitivity is limited by quantum noise, random fluctuations in the number of photons detected. By generating squeezed states, in which the uncertainty in one property, such as phase, is reduced at the expense of increased uncertainty in another, such as amplitude, researchers can push the sensitivity of these instruments beyond the classical limit. This technique has already been implemented in gravitational wave observatories, contributing to the detection of signals from colliding black holes and neutron stars, and promises to enhance a wide range of optical sensing applications. Another area of intense research is quantum imaging, which leverages quantum correlations between photons to achieve imaging performance beyond what is possible with classical light. Techniques such as quantum ghost imaging, quantum lithography, and subshot noise imaging exploit the non-classical statistics of photon pairs generated by processes like spontaneous parametric downconversion. These methods can produce images with higher resolution, lower noise, or enhanced contrast, opening up new possibilities in microscopy, remote sensing, and biomedical diagnostics. Quantum sensors are also finding applications in chemical and biological sensing. By using quantum states of atoms or molecules as probes, it is possible to detect trace amounts of chemicals, biomolecules, or pathogens with extraordinary specificity and sensitivity. For example, quantum-enhanced Raman spectroscopy uses entangled photons to improve the detection of vibrational modes in molecules, enabling the identification of substances at concentrations far below the limits of classical techniques. Similarly, quantum sensors based on trapped ions or cold atoms can be used to study chemical reactions in real time, providing insights into fundamental processes that govern life and matter. The integration of quantum sensors with other emerging technologies is creating powerful synergies. For instance, the combination of quantum sensing with artificial intelligence, AI, and machine learning enables the extraction of meaningful patterns from complex, high-dimensional datasets generated by quantum measurements. AI algorithms can optimize the control of quantum systems, correct for noise and errors, and identify subtle signals that would otherwise be lost in the background. This interplay between quantum and classical information processing is opening up new frontiers in data-driven discovery and decision-making. Quantum networks, which connect quantum sensors over long distances via entangled photons or other quantum carriers, are another exciting development. Such networks could enable distributed sensing, in which an array of quantum sensors works together to measure global properties of a system or environment. For example, a network of quantum gravimeters could monitor seismic activity across an entire continent, providing early warning of earthquakes or volcanic eruptions. Similarly, quantum sensor networks could be used to synchronize clocks, detect gravitational waves, or search for exotic phenomena with unprecedented reach and coordination. The miniaturization and integration of quantum sensors onto chip-scale platforms is a major focus of current research. Advances in nanofabrication, photonic circuits, and materials engineering are enabling the production of compact, robust, and scalable quantum devices. These developments are critical for translating the extraordinary capabilities of quantum sensors from the laboratory to real-world applications, where size, weight, power consumption, and cost are key considerations. Already, chip-scale atomic clocks and magnetometers are being developed for use in mobile devices, autonomous vehicles, and other portable systems. The commercialization of quantum sensors is gathering momentum, with startups and established companies alike entering the field. Market analysts predict rapid growth in the quantum sensing sector, driven by demand in areas such as defense, aerospace, healthcare, environmental monitoring, and industrial automation. Governments are supporting these efforts through targeted funding, public-private partnerships, and the establishment of innovation hubs and testbeds. As the ecosystem matures, standards, certification processes, and supply chains are being developed to ensure the reliability and interoperability of quantum sensor technologies. Ethical and societal considerations are increasingly coming to the fore as quantum sensors become more pervasive. Issues such as data privacy, surveillance, and dual-use concerns must be addressed proactively to ensure that the benefits of quantum sensing are realized in a responsible and equitable manner. Policymakers, ethicists, and technologists are beginning to engage in dialogue about the implications of ubiquitous, ultra-sensitive measurement capabilities, seeking to balance innovation with respect for individual rights and societal values. In education, quantum sensors provide a compelling context for teaching core concepts in physics, engineering, and information science. Hands-on experiments with quantum devices can inspire students, demystify abstract principles, and cultivate the skills needed for the quantum workforce of the future. Outreach initiatives, public lectures, and interactive exhibits are helping to raise awareness of quantum technologies and their potential to shape the world. As we look ahead, the trajectory of quantum sensors suggests a future in which our ability to measure, navigate, diagnose, and explore is limited only by our creativity and ingenuity. The convergence of quantum science, engineering, computation, and data analytics is opening up new horizons for discovery and innovation. Whether in the search for new physical laws, the quest for better health and safety, or the drive to build smarter and more sustainable societies, quantum sensors are set to play a central role. In conclusion, quantum sensors epitomize the transformative power of quantum mechanics when applied to real-world challenges. Their unique combination of sensitivity, precision, and versatility is already yielding tangible benefits across a spectrum of domains, from navigation and healthcare to environmental stewardship and fundamental science. The journey from laboratory curiosity to ubiquitous technology is well underway, propelled by advances in materials, devices, systems, and applications. As we continue to unlock the secrets of the quantum world, quantum sensors will remain at the forefront of human ingenuity, enabling us to perceive and understand the universe in ways that were once thought impossible. The age of quantum sensing has arrived, and its impact will be felt for generations to come.